It's a pleasure to introduce Sabrina. She was here already visiting us more than 1 year ago, so I will just give a very brief introduction. So from 2011 she's leader at the Heriot-Watt University in Edinburgh. She's also deputy director of the Institute of Photonics and Quantum Sciences. Thank you. And she obtained a PhD in Palermo in 2004. And then she was postdoc in several places. She was in Bulgaria, in South Africa, in Finland, and now she's in UK. And she's been working in trapped ions, quantum optics, quantum information. She's well known for questions related to non-Markovianity quantum systems. And she also has a large experience in outreach activities. We were present at the projection of the quantum circus we had also in the last visit. She also organized a series of lectures for non-physicists, a series of programs in the radio, and she was also producer of a documentary Inside the Light in 2009. 2011. Okay, so today she will tell us about non-Markovianity as a resource for quantum economics.
Thank you very much, Roberta. It's always a pleasure to be here, and thank you for a very nice introduction. So I will talk about non-Markovianity, in particular in quantum systems, and this doesn't have a strong connection with non-Markovianity in the classical sense, so non-Markovian stochastic processes, but it's been extensively used for reasons that will be clear, I hope, during my talk, for understanding the dynamics of open quantum systems, so quantum systems interacting with their environment, What I would like to do is to, first of all, to explain better in which sense I'm using the term non-Markovianity and why we should be interested in such a concept in the framework of open quantum systems. And I will do this by, I decided to have some sort of historical approach, again, within the framework of open quantum systems. And obviously, first of all, I have to define the type of systems I'm looking at. And is that a pointer? Maybe it is a pointer, exactly. Maybe. So the whole idea that we consider is a closed total system composed of two parts. The quantum system, that is basically by definition what we are interested in, and the environment, and generally I will discuss the case of quantum environments. And the quantum system interacts with the environment in a certain way, and I want to describe the time evolution of the quantum system during the interaction with the environment, so subjected to an interaction of the environment. But my object, the main focus will be the quantum system itself, so I will basically trace out all the degrees of freedom related to the environment. Now, within the theory of open quantum system, the major division, let's say, when studying the dynamical properties, is between what people call Markovian open quantum systems and non-Markovian open quantum systems. And yeah, I'm listing some usually, I would say in a hand-wavy way, but in an intuitive way, definitions of what people mean, what the quantum information and open quantum system community mean when talking about Markovian and non-Markovian open quantum systems. When talking about Markovian system, generally people assume that the correlations between the system and the reservoir or the environment, I will use the term reservoir and environment in the same way. Obviously, the reservoir is more specific than environment, but allow me to use both in this instance. So when correlations between system and environments are negligible, or when they live for a very short time, and we really don't consider the short time environment, so we course grain over time. This is an example of a type of Markovian dynamics. People talk about Markovian dynamics also saying that there is absence or negligible environmental memory effect. So some people refer to this type of dynamics as memoryless dynamics. And also other people say that one has a Markovian evolution when the spectrum of frequency of the environment is more or less flat. It doesn't have strong structural peaks. And finally, again, people say that for Markovian open quantum system, the master equation, that is the equation of motion for the density matrix, describing the state of the open quantum system, has a specific form known as the Lindblad form. I will go in more detail, on all these points, so perhaps you will understand them better. But I just wanted you to start by listing simply what people generally mean when talking about Markovian open quantum system. Of course, non-Markovian are just put a non in front of that, okay? So you have non-negligible system reservoir correlations, non-negligible environmental memory effects, structured environmental frequency spectrum, and of course the master equation is not or cannot be recast in the Lindblad form. Now, it's important to say that all these sort of properties are not equivalent, okay? They mean different things. So I just want to confuse you to begin with. It's complicated, and people had also issues with language. Different communities refer to non-Markovian dynamics meaning different things. Okay, so one of the main aim historically was to find or to agree on a definition. Okay, so this was one of the main issues of what we will do. But again, from the perspective of quantum optics, master equations that are, again, equation of motion for the density matrix of the reduced systems have been extensively studied. And in particular, the most famous form of master equation is the one in the Lindblad form, and is written in terms of a commutator between the density matrix of the system and the system Hamiltonian, and a second term that is known as the dissipator. This part takes into account non-unitary losses due to the interaction with the quantum environment, and is composed of several operators that are known as the jump or Lindblad operators, and this constant here, the gamma k's, are the so-called decay rates. If I have k decay channels, I will have gamma k decay rates. As I say, this has been extensively used, for example, to study laser cooling in quantum optics, but not only. Instead of describing the dynamics in terms of a density matrix, again, representing the state of the system, one can use a stochastic description in terms of single state vectors, known as quantum trajectories also. And in this case, the dynamics of the of the state vector psi I is subjected to a non-Hermitian Hamiltonian interrupted by stochastic jumps that are due to the, or related to the decay described by the decay rates gamma k. And one can prove that this description is equivalent to the density matrix description if I take an ensemble average of all the vector realizations. So I have, this is known as master equation unraveling, what basically means is that I have a way of describing an open quantum system in terms of a stochastic process in the Hilbert space, basically. So they are equivalent descriptions. And this was formalized in particular, again, within the quantum optics community by what is known as the Monte Carlo wave function approach, developed by, among the others, by Marc and Dalibard in 1992. Now, the important point I want to make here is that if one uses quantum trajectories, then one can interpret the dynamics of the open quantum system in a physical sense, in a way that each quantum trajectory describes the dynamics of the system conditioned to continuous measurement on the environment. Okay, so it's as if I'm measuring or observing continuously the environment. I don't read the result of the measurement, but this is the physical interpretation of a quantum trajectory. Now, the key point to understand, or that allows actually this measurement scheme interpretation of the dynamics, is the fact that when I look or when I describe master equations in Lindblad form, I'm sort of assuming that if I measure the environment, I'm not perturbing the system. I'm measuring the environment or observing the environment continuously, but again, I'm not reading out the result of the measurement. And this assumption is something that holds really, actually it's justified whenever a system can be described in terms of linear master equation or Markovian master equation. But we will see that, in fact, this is not the end of the story, and otherwise I would finish my talk here. But no, actually my talk is about to begin, indeed. Markovianity is not enough. Within the framework I described before, so total closed system, divided in two parts, system plus environment, in some cases it is possible to solve exactly the dynamics of the total system and then trace out the degrees of freedom of the environment. And one can see that actually the exact dynamics, so the master equation of the reduced system in the exact case, is not of Lindblad type. So Markovianity or a Lindblad-like master equation is always an approximation. All quantum systems described within this formalism are non-Markovian in the sense of non-Lindblad. So they are not described by in exact terms, in exact ways, okay, by the Lindblad master equation. This is exactly what I said before. And some quantum effects that indeed require this non-Markovianity, these deviations from Markovianity, are quantum Zeno effect, dynamical decoupling, membrane techniques. So there is a variety of quantum effects and properties that strongly rely on the fact that initially, if I look at short times, I can never have exact Markovian dynamics. Now, you may be familiar, for example, of one of the simplest examples related to the quantum Zeno effect is the Fermi-Golden rule. So, in the case of spontaneous emission or spontaneous decay, the assumption that the decay initially is linear or exponential, in general, in the Markovian case, it's just an assumption, and all quantum systems start decaying quadratically, which is the reason why quantum Zeno effect indeed exists. Now, that said, in order to describe what is beyond the Lindblad master equation, I need to introduce the concept of divisibility of the dynamical map. So a dynamical map for an open quantum system is an object, is a superoperator that, given an initial quantum state, tells me the final state or the state at time t of the system. So it's a completely positive and trace-preserving map, and basically it's an alternative way of describing the dynamics rather than the master equation. One can use obviously both descriptions. Now, divisibility is a property of the dynamical map that can be written in this way. So a dynamical map is said to be divisible if I can decompose it in two maps in this way. So lambda 0 is my initial time. So the dynamical map from 0 to t can be decomposed in a dynamical map from 0 to s, where s is a time instant smaller than t, and the dynamical maps from s to t. Okay? What I'm assuming here is that this object and this object are also completely positive and trace-preserving. Okay? So this is true. This property says that this completely positive and trace-preserving map can be decomposed for all times s, whatever is the intermediate time s, into the composition of two completely positive and trace-preserving maps. And one might think that this is basically always the case, and indeed, this is not true. So indeed, it's wrong. So this is not always the case. And this is actually where the interesting story begins. Now, if I have a dynamical map, so an evolution of an open quantum system which is divisible, then I can still use the Monte Carlo wave function approach, and I can still interpret the dynamics in terms of an evolution of a quantum state conditioned on a measurement of the environment. So Monte Carlo wave function and the measurement scheme interpretation apply straightforwardly in the case of divisible systems. What happens is that, well, before saying what happens in the case in which this is not true, whenever I have this property, then I can rewrite the master equation. Here I'm writing only the dissipator. I'm neglecting, let's say, the unitary part. So this is the dissipator appearing in the master equation. In terms of decay rate that are now positive but time dependent. So in the Lindblad form, these objects were positive and constant. Now we have positive but time dependent decay rates. And again, the interpretation continues to be valid completely as before. However, in some cases, there exist completely physical dynamical maps for which this property is not satisfied. So this means basically, for example, that I cannot find a completely positive and trace-preserving map, or I cannot combine this completely positive and trace-preserving map in terms of two CPT maps, completely positive and trace-preserving, for some time s. Okay, there exists a time s for which I cannot write this. And in this case, what happens is that if I look at the master equation, the decay rates become temporarily negative. Not always, they generally, or always actually, start with a positive value, but they evolve in time, and they take for some intervals of time negative values. So what's the meaning of negative decay rates? What one may ask. Well, first of all, it's important to say that in this case, there is still what perhaps is the most, one of the most important open problems in the theory of open quantum system, and this is whether there exists, connected to the question of whether there exists a measurement scheme interpretation, which means basically whether I can see, as I did before, the dynamics of the system, of the open systems, in terms of state vectors conditioned on measurement on the environment. There has been actually a lot of results and debates. I remember, I think it was in 2008, we organized a small workshop in Turku. At that time I was in Finland, and there were many people working on non-Markovianity, among them Lajos Diossi, and what his thought was exactly, he believed that he solved the measurement scheme interpretation problem, and therefore it was possible to give a measurement scheme interpretation. And then after a while, he published a paper in Physical Letters, and after a while there was another paper by Weismann and Gambetta proving that there was a mistake in his solution. So it is still unknown whether it is possible or not to find an unraveling that is physical for non-Markovian open quantum systems. But of course,
excuse me,
yes.
Because you have warned us at the beginning
yes.
that non-Markovianity was something very well defined in classical stochastic processes, and here it is not. But then you keep talking about the debate, the discussion,
yes.
about something that you have not yet defined.
Yes, it's true.
So what is the discussion or the debate? What's the definition?
Yes, that's a very good point. What I discussed here is a very good point because perhaps I forgot, since I wanted to give you an historical perspective, I assumed obviously something that I didn't have to assume. So historically, in the quantum optics commission, the definition of Markovianity was the definition of Lindblad form. So everyone thought that I could, let me see, I could, it was, yes, by definition, Markovian dynamics was a Markovian in which I could write down an equation of motion for the open system in a form that is this one.
Markovianity was associated not to a particular form, not to a particular type of equation, but to a particular form of the equation.
To a particular form of the master equation, or equivalently to a property of the dynamical map that is the semi-group property. It's very similar to divisibility, basically, but only for me. So this was the definition of the quantum optics community.
I mean, if we go to historical things just to understand the way of reasoning of these people, I just cannot think that if you write the general evolution equation with your gamma t, someone would assume that necessarily any gamma t could be written as a solution of this equation.
Any gamma of t, in which sense? Any of this? Or in lambda? The dynamical...
Lambda, I'm sorry, lambda.
No, in fact, it is possible because you can, basically the analogy is with the, let me write it here.
But I mean, this is a very specific form of this.
No, it is not. I mean, one of the main results obtained by both Lindblad and Gorini-Kosakowski and Sudarshan. So there was, in 1974, a theorem known as the Lindblad theorem, but also equivalently demonstrated by Gorini-Kosakowski and Sudarshan. And this is connected to the following. I will write something in a very, let's say, hand-wavy way, but allow me to do this. So basically, if I have something which is written in this way, this I have t, and here 0.
Yeah, this is a linear equation in Hilbert space.
This is a superoperator, okay? So it's a superoperator, so it is basically, I'm writing here the same thing as C, okay? So here there are operators C, C, and...
Yeah, but this is a specific form.
No, the phi, yes, yes, but this is not time dependent. So if I write the phi of t, which is the dynamical map, in this case, which is the generator of this master equation, I can write it in this way, the generator of the evolution. And so therefore I can write, so this specific form of generator of the evolution satisfy the semigroup property. Now, whenever I have, by definition in the quantum optics community, whenever I can recast either the dynamical map in this form or the master equation in this form, I will define this as a Markovian open quantum system. And the reason why people did this is that in quantum optics, if you take any master equation in quantum optics, they are all having this form, all of them. The reason I was talking...
so do I understand the definition that some people gave of Markovian quantum system is that the dynamics can be written like that without being independent of time explicitly? Is that the definition?
You can, basically, you can incorporate also time dependency, but yes, this is the definition. But the reason it's...
No, yes or no? What's the definition?
No. You can incorporate time dependency in the sense that you can have Hamiltonians which are time dependent, okay? So here, I only use the L, okay, the dissipator. Obviously, I can use what I call the Liouvillean, which takes into account also this part. I can do it, everything, it doesn't change much. I only obviously have to introduce the time ordering operator, but it doesn't change the essence. So this is in this sense, yes or no. Now, a small, meaning that in this case, if these are not time dependent, but are positive constant, this is what people defined as Markovian. Of course, I can, as I said before, use time dependencies in the Hamiltonian here, and then I would define a superoperator, which is the Liouvillean, which takes into account this part. But really, the unitary part is not the issue in the definition, obviously, of Markovian versus non-Markovian. Now, it may seem reductive, but if you look at all quantum optics, really, always and only deals with master equations in this form. It was perhaps, I think, 3 years ago, I was visiting, I don't know if you know Lindblad, Goran Lindblad, they're working at KTH, and I was giving a seminar there, and after the seminar I talked to him, and I asked him, okay, how come you came out with this, this is known as the Lindblad theorem, it's precisely the theorem that demonstrates that you can always recast the master equations in this form if it is a semigroup. And the reason why he's a mathematician. The reason, the answer that he gave me is I was looking at physics papers and I only found equations of motion in this form. So I started to wonder what are the physical properties of this equation? Why all the physicists are only using these equations when describing dynamics? This was his answer. And he came out with a theorem that is a theorem that proves that basically if I have a linear map that satisfies the semigroup property, then necessarily the master equation will have this form. It's known as the Lindblad theorem, and is one of the main results. Now, a step further, this can be reductive, but well, then all quantum optics fits into this category. Now, a small, let's say, change is the case in which I have decay rates which are time dependent here. It doesn't really change much. Okay, if I have time-dependent decay rates, as long as they are positive, okay, all the physics and the phenomenology, even the mathematics, basically remains unchanged here. Of course, in the linear map, I have to define something like this, whatever it is, and I have to have time ordering, but it doesn't change. As long as these decay rates are positive and this is the form, I'm happy. There is no change in the phenomenology. This was the definition. Now, I will show you in a moment what happened after, because people were not satisfied, perhaps like you, were not satisfied at all with this definition. They said, we don't like this.
No, I was not satisfied with not having a definition.
Okay, so I gave you now the definition, but I will tell you that this definition is generally not satisfactory, or was not thought as satisfactory for many people. The reason why it wasn't thought as satisfactory, one of the reasons at least, is the fact that, first of all, it is not easy, because the definition says that the master equation should not be, it is impossible to recast the master equation in this form. Generally, it is not easy to see when and how one can recast a master equation in a given form. In some cases, it is really not simple. And the other issue is related to the fact that in this case you need to rely on a form of master equation, and sometimes you don't even know what is a possible form of master equation. So the idea was, what I will say in a moment, to change, let's say, the discussion and try to define in a different way. And I will do it in a second, but before. Okay, now I gave you definition number 0. Now, definition number 1, we need to fly a little bit. Now, definition number 1 is exactly the same as before. However, this time I will call Markovian something which has time-dependent decay rates, but positive, okay? Number 0 historically was constant positive. Number 1, time-dependent, but positive, historically. And I will skip the measurement scheme interpretation and the quantum trajectories. What happened is that in this case, people started to wonder, okay, if this is an equation of motion, where is memory? Where is the memory effect in a time-local master equation? The future of the state depends on the state at time t. It does not depend on its past. Where is the memory there? Okay, this was really, let's say, one of the main concerns. And I will just briefly say that what happens is that if you extend, we did extend the Monte Carlo wave function approach to the non-Markovian case, with including the case of negative decay rates, and you can find out an unraveling, so in terms of quantum trajectories, that allow you to understand what happens in the stochastic description, but requires the introduction of an object, that are the reverse jumps, that cancel the previously occurred jumps. So the memory shows up in two ways. The first way is the fact that you have some objects that tell you the previous jump did not occur. So they cancel previously existing jump. This means simply that the quantum jumps become virtual processes, basically. And the second way in which the memory is introduced is in the fact that all the trajectory, in fact, become not independent, but they depend on each other. But I will not have really time to discuss this in more detail. Now, at this point, several people started to think, is there another way, another definition, if you want, to characterize non-Markovianity? And this is the time, I think it was the first paper which was proposed and introduced in 2009 by these authors to define non-Markovianity, or try to define non-Markovianity in terms of information flow. So their idea was, we want to characterize memory effects, and so we assume that we can describe the amount of information that we have on the system flowing from the system to the environment and then back. So this backflow of information should be connected to memory effects. So what they tried to do, what they had in mind, was to connect information backflow to the presence of reservoir memory, or if you want, to non-negligible correlations between system and environment. And they did this in terms introducing the concept of state distinguishability. So what I will do now is to describe briefly this measure, which was the first definition and also measure of non-Markovianity, the BLP non-Markovianity, and then I will comment on some of the drawbacks actually of this measure and propose another way of quantifying non-Markovianity that is this time related to quantum technology. So it uses a quantum information approach. Okay. So, questions? No. Now, the idea, the mathematical objective or measure that they used is the trace distance between two quantum states. So they consider a pair of quantum states, and they define distinguishability between the two states, as it is defined in quantum information theory, for example, as the trace norm of ρ1 minus ρ2. And this trace distinguishability has an important property that is the one that is described here. So it is contractive. So if phi is a dynamical map, so a completely positive and trace-preserving map, the distinguishability between two states, and if I compare the distinguishability between two states at the initial time and at the final time, after a time t, always the final distinguishability is smaller than the initial one. So the distinguishability decreases generally for any trace-preserving map. It's called contractivity of trace distance. What they did, therefore, is to define a rate of change of the trace distance, and now they looked, or they defined non-Markovianity in terms of the, by the way, this is known as, here, as the information flow. They called this quantity the information flow, and then they want to see when the information flow is positive or negative during a time interval. And now this is a definition, the definition that they gave of Markovianity is the following. Whenever I have a situation in which the derivative of trace distance is smaller or equal to 0, so it's negative or non-positive if you want, for any time t, then I will call this process Markovian, and I will see this, I will interpret this as a situation in which information flows away from the system, so the information lost from the system to the environment continuously, okay, without anything coming back. Instead, if there exists time intervals for which I have partial regrowth of information, so if I have positive values of the information flow, I will talk about define this as non-Markovian dynamics, and I will characterize this idea in terms of a backflow of information. This was the paper of 2009 that's been then extensively used even in experiments and so on and so forth. So this is the definition. Associated with the definition, there is a measure. What they want to do is obviously a measure of non-Markovianity has to be independent on the initial states. It has to characterize only the dynamical map or the quantum channel. So therefore, they take an integral over all the periods in which the information flow is positive. And obviously this still depends on ρ1 and ρ2, the pair of states, initial states considered. So they have to maximize over all possible pairs of initial states. So now this is yet another definition of non-Markovianity. This currently is the most used definition of the non-Markovianity in open quantum systems. Most extensively used. Of course, by definition, when this number is 0, I have Markovian dynamics and monotonic decrease of trace distance. When this number is non-zero, then I have revivals of the time distance and Markovian dynamics. Now, what is the connection with the divisibility property that I introduced before? Okay? To answer to this question, in this slide, I list 5 different where these two are connected. So 1, 2, 3, 4. There would be another one recently introduced by Francesco Plastin that I didn't list. 5 different new definitions or measures of non-Markovianity that have appeared after 2009, just to look at the proliferation. So they're all based on a concept associated to non-monotonicity during time evolution of a certain quantity. The first one in 2009 was non-monotonicity of trace distance, so something which comes back in time. Then there was in 2010 non-monotonicity of entanglement between a system and ancilla. This is the Rivas-Huelga Plenio measure. In terms of Fisher information, again, non-monotonicity of the Fisher information, non-monotonicity of mutual information between system and ancilla, and so on and so forth. So there's been an explosion of different ways of quantifying and at the same time defining, okay, non-Markovianity, if you want. The connection with divisibility is that all these measures, whenever one of these measures tells me the system is non-Markovian, so I have a non-monotonic behavior, then this means that the dynamical map is non-divisible. The inverse is not true. So they're not equivalent to non-divisibility, but non-Markovianity, according to any of these, implies always non-divisibility. Okay? So there is some sort of benchmarking type of property. Now, you can be very unsatisfied by the fact that people are using all these different measures, they do not coincide, so after all, what are we looking at? But this is just a reflection of the fact that we are trying to describe a complex, not in the sense of complex systems, a complicated, if you want, and a complicated phenomenon that has to do with system and reservoir, trying to describe a general, or use a general formalism, but which in fact is related to several issues. It's related to structure of the environment, it's related to system-reservoir correlations, can be related to the presence of, for example, band gaps in the structures. There can be several different aspects that lead to behavior that can be associated to non-divisibility, but not unique. So basically, reservoir memory may have different effects on different dynamical properties, which one may want to harness for certain specific purposes. Okay, now I'm going to criticize, to make a critique of one of the things that I said many times in my talk, and also in this talk, and this is the concept that was introduced by the definition of non-Markovianity, and this is the fact that we are used to say that the non-Markovianity defined in terms of trace system quantifies the amount of information on the system previously lost in the environment and which flows back during the memory. So we sort of assume that what happens is I have information on the system, it goes into the environment, then it partly comes back, then it is lost again, then it partly comes back. Now, my claim is that this, there is no reason, actually, mathematically, why this should be the case if one uses the trace distance measure. The reason is that what trace distance quantifies, and this is really a commonly, the trace distance is a commonly used measure of information in quantum information theory. It quantifies the amount of information I have on the system. It doesn't say anything at all about the amount of information of the environment or the change of information on the environment. Besides, we have to also clarify what we mean with information itself. And indeed, what we did with in collaboration with Bogna, Pilicka, and Darius Lushitsky was to try to answer to the following questions. What do we actually mean with information? How do we quantify it? And are we really allowed to talk in terms of flow of information from the system to the environment and back when using the BLP measure? And also, obviously, is the information that flows back the same, into the system the same that has been leaving into the environment? So our main goal was to re-examine the concept of non-Markovianity, however, looking at the core principle and ideas of quantum information theory. As quantum information theory is a well-developed field, we wanted to use a quantum information way of quantifying information on a quantum system. Now, going back really to study from books of and Chang and so on, one of the key properties of quantum information theory, or actually information when described or encoded into a quantum system, is its hidden nature somehow, which is reflected in the no-cloning theorem and basically consists, or one can see it, as a statement that the accessible information that we have on a quantum system does not coincide with the entropy of formation. So necessarily the quantum information has some sort of hidden nature. And generally, there are no ways of calculating the accessible information. Of course, there exist useful bounds, and I'm going to discuss about some of these bounds. The level bounds is in the classical case for classical channels, and I will introduce bounds for the quantum channel. So let me reframe let's say, the definitions or the general approach of open quantum systems in terms of quantum channels that are what generally people use in quantum information theory. So a quantum channel is basically the same thing as a dynamical map, with the only difference now I have time. So actually the dynamical map is a T-parameterized family of channels, so completely positive and phase preserving map. And I'm not changing, so the map is always the same. I can't change the phi because physically I will always have one dynamical evolution. So it's a T-parameterized family of quantum channels, and now I have an input state and an output state. One of the ways of quantifying the amount of accessible information I have in the output on the initial state, when the system travels along a noisy channel, obviously I'm considering quantum channels, not noiseless, but noisy quantum channels, because I'm describing open quantum systems here. So a way of quantifying the accessible information on the initial state that I have at the output of the channel when noise is present is using the quantum mutual information between the input and the output state. Now, this is defined in the following way. I have the entropy of the input state, the entropy of the output state, and what is known as the exchange entropy of exchange, which is an object that I don't write explicitly. It is defined in terms of the so-called complementary channel. If you are interested, I will define it. But the main point here, the main message is that the exchange entropy physically corresponds to the variation in entropy of the environment. Okay? So now I have an object which links the entropy of the output state, the change in entropy of the environment, and this is what I want. Obviously, this object, the entropy of the initial state is a constant, and in any case, we'll see, we'll be maximized eventually. But now I have a quantity that contains information about the lack of information, if you want. These are von Neumann entropies, obviously. So the lack of information of the output state and the variation in entropy, which can be associated with under our principle of information, change of information. And now I can define, I can use what is one of the most extensively used concepts in quantum information theory, and these are simply the concept of capacity. And I start introducing the entanglement-assisted capacity, which is defined in terms of the quantum mutual information by taking the supremum of the input state. Okay? So this object now characterizes only the map, is independent of the initial state because of this operation, and has a well-precise operational interpretation, and physically this gives me a bound on the maximum rate at which classical information can be sent through a noisy, reliably sent, through a noisy quantum channel when Alice and Bob, means input and output, share unlimited entanglement. Okay? So this is basically a quantity that characterizes how well, for example, I can perform quantum correction, quantum teleportation, distribute quantum distributed entanglement in networks, and all these things. So basically, because it tells me how good is the rate at which I can send classical information along a quantum channel. Okay. Is this clear? This is just a definition. And here, Alice and Bob, of course, are always the input and output states of the channel. I can also define the quantum channel capacity for single use, so assuming that I only send the information once. And this is a very similar definition. In this case, I'm introducing this object, which is known as the coherent information, which is equal to the mutual information that I defined before, minus the entropy of the initial state. Okay, it's the coherent information. And now, it has been proven that this quantity gives me a bound on the maximum rate at which I can reliably transfer quantum information along a noisy quantum channel. Okay? Now, I'm interested in these two quantities, and how much time do I have? 5 minutes? 10 minutes? 10 minutes. Now, One of the main results of quantum information theory is the data processing inequality that for divisible channels tells me that the quantum channel capacity monotonically decreases in time, basically. Okay? This is true, however, only for divisible channels. It's true both for the quantum channel capacity and for the entanglement-assisted capacity, but this is in fact a property of the quantum mutual information. But in any case, the data processing inequality implies this relation and this relation. And now, intuitively, this means that from the point of view of the efficiency of transferring quantum information, the more I process the data, the worse it is due to noise. Okay? I want to that my data is less processed, because processing data means basically destroying quantumness that I want, all the quantum information that I want to transfer. Therefore, one can think of associate, because this is related to divisibility, and divisibility is the benchmarking property of non-Markovianity, as we said before. I can now define or look at situations for which the non-Markovianity will be associated to a non-monotonic behavior of the channel capacity, so of the quantum channel capacity or the entanglement-assisted capacity. So now I don't have to optimize anymore here, because I optimized before. I mean, it was in the definition of the channel capacities, it was out of an optimization. And in this case, so basically I simply consider the intervals of times when I have a regrowth and I sum them up. Now, this is the first message that I want to give. And I believe that from an interpretational point of view, if we want to characterize memory effects in terms of backflow of information or something that has to do with information exchange between system and the environment, I think that we need to use a definition that relies on a quantity that links the information on the system with the information on the environment. Or if you want, in our case, in an entropic way. In our case, the quantum mutual information links the entropy of the output state, so of the evolved state, with the change in entropy of the environment. Okay? And I believe that from an interpretation, which was the original motivation of Royal Line-Apilo and other people in particular, was exactly to try to physically interpret or physically associate memory effects with backflow of information or exchange of information between system and environment. Now, here, one of the nice properties is that I think that this can be done by using the channel capacity definitions. It has a nice operational interpretation, as I discussed, and it's, they are quantities that are extensively used to discuss the efficiency of error correction protocols and quantum communication in general protocols. And of course, in some sense, they characterize some resources in quantum communication and quantum information processing. Now, I want to give other three nice properties, and then I will conclude with three simple examples to show what are the advantages of, what we can learn from this description. The first nice property is that this measure, in particular the entanglement-assisted capacity measure, and in some cases, so NC, and in some cases NQ, the quantum capacity-based, both of them are additive. What I mean with additive is the following. If I have, say, n qubits, so 1, 2, 3, n, each of them interacting with independent environments, okay? So not with common environments, but independent environments. And I assume that this interaction is the same, so n identical independent environments. Then I can calculate the total non-Markovianity, and this is exactly equal to n times the non-Markovianity of the single channel. Okay. This additivity property is not satisfied by any other measure. So the Royal-Line-Apilo measure, the Fisher information measure, they are not additive. The fact that they are not additive makes it basically impossible to calculate them for more than 2 qubits in any circumstance. So until now, the only examples that have been done is up to 2 qubits. 2 qubits is the limit, and only in spatial, very simple circumstances. Of course, you can do it also for continuous variables, but let me focus on the qubit case here. But also there, I mean, you really have to really calculate them. You have to restrict a lot the space for the optimization. Now, this is not the case for our measure, because I can obviously easily, trivially actually calculate the non-Markovianity of n qubits, because it's just in these conditions n times the single qubit non-Markovianity, which is useful. If you think that non-Markovianity is a resource, then you want to see how good it is to have non-Markovianity when I have n qubits rather than, because you want to go in for realistic scaling of the systems, rather than just limit yourself to the 1 qubit case. It is really a sort of textbook, not textbook, but just an example to explain this type of phenomenon. I talked about the operational interpretation. No, I'm back somehow, I don't know why. I was playing with this. So it is easier to calculate. I have to optimize over one state rather than two. Seems a little thing, but again, in some cases it can make a lot of difference. And also it's able to distinguish between different types of resources. It's easier to transmit classical information than quantum information, and indeed you will have that this measure is different from the other one as it should be. I conclude with a few examples, 3 examples, very simply. The first one is the so-called dephasing channel. I have just 1 qubit subjected to pure dephasing noise, so it only affects the off-diagonal elements, the populations remain the same. And this is a master equation with only 1 decay rate. The model is exact, so there is no approximation here. You can solve it exactly. So the time-dependent decay rate is initially positive and then becomes negative. The quantum channel capacity initially decreases, but then increases again until it reaches a stationary value. So this is an example of a non-monotonic decay of quantum channel capacity associated to the negativity of the decay rates and therefore to divisibility. The second example is a more complicated channel. This is called amplitude damping channel. In this case, I have dissipation. It's not just pure dephasing. I have dissipation, again, for 1 qubit, 1 two-level system, into a 0 temperature reservoir. I assume, so basically it's a 2-level atom with ground and excited state. For example, interacting with a Lorentzian, so this is a J of omega. A bosonic, imagine this could be a cavity field, so the spectrum of the electromagnetic fields inside the cavity. And now I have, if I look at the quantum capacity as a function of time for different values of non-Markovianity, the blue line is this one. Then I have the red line. I go increasing the value of non-Markovianity. As you can see, the channel capacity is all. First of all, there are oscillations, but I have higher value of the quantum channel capacity, which means that these examples, let's say, this value, this situation is better than the other one. So in this case, I have non-Markovian is better than Markovian in all these examples, basically, because I have a higher value of quantum channel capacity that allows me to do more communication processing tasks. And finally, the third case is the case of a photonic band gap, very simple actually. It's a toy model of photonic band gap material where the spectrum has this form. So again, the J of omega is flat and then if I go this here, and then it goes down. It was 1 over square root of omega minus omega. So it's just a toy model used in certain papers just to illustrate some of the features of these systems. And what you can see is that for different values of non-Markovianity, if I focus, for example, on the highest non-Markovianity value, I have a phenomenon known as quantum capacity trapping. So eventually the quantum capacity will not disappear, so it will not become 0, as it would happen in all Markovian systems. So for Markovian decays, the quantum channel capacity at some point, after a certain time, becomes 0. It means that the channel is useless. I can't use this channel for quantum communication purposes. Okay? While here, in this non-Markovian case, if I modify the spectrum of the reservoir, I can engineer a situation in which the channel capacity remains constant, basically forever, as in the previous slide. So summarizing, I can have an increase of the channel capacity for a given channel length. So the channel capacity remains non-zero for longer lengths of the channel in the non-Markovian case, when compared with the Markovian dynamics. I can have revivals of the channel capacities, so a longer channel can be better than a shorter channel for quantum information protocols, because the quantum capacity at a later time, or at the extreme end of the channel, can be higher than the channel capacity that I stopped before, it was a smaller channel. And I can have length-independent finite capacity channels. So I can have situations in which the quantum channel, if I properly engineer the frequency spectrum, and I make it non-Markovian in the sense of the quantum channel capacity, I will have situations in which whatever is the length of the channel, it could be an optical fiber, for example, the channel capacity will be positive, non-zero, and constant, in contrast to the Markovian case. I think that was all. I thank you for your attention, and I have a question.
Any questions or comments?
No, just a curiosity about one of the last plots. You make a comparison with the other measures, but they...
Yes, we do have. We do have in the paper a comparison with the with three measures actually, with the river Scoringa plane and no. In the paper there is only the VLP measure and the LUO measure, so the mutual information measure. Now, if you look at the, for example, VLP measure, what happens is that the conditions for non-Markovianity of the channel capacity is stronger. So it means that it can be non-Markovian according to VLP, but still Markovian in terms of channel capacities. So you need more, let's say, more memories, if you want, to have revivals of the channel capacity. So broadly speaking, this is what we saw basically all the examples.
I have a question related to this, so then yes. What did you change to go from one to the other? How did you change the shape of the spectrum to go to one?
I think in this case of the photonic band gap, we just changed the distance to the edge. So if this is the frequency of the edge, we were more in the gap port, less in the gap port, more outside of the gap. So the detuning rather than. So it was a change simply related, not to the frequency spectrum, but to where the two-level system, if you want, the atom is positioned in the spectrum.
And then the question is, would you say that there is a causality relation between, I mean, do you think that is the non-Markovianity defined as this sort of information that is really causing the different behavior, or they just happen to be together?
The different behavior means the trapping.
For instance, in the three things that you are showing, the three examples, do you think that each of them is really the non-Markovianity that is causing the effect, or they just happen to be present together?
No, I mean, the thing is, if I define, it depends. I don't know if I understand well the question. The question is, my starting point is I want to preserve channel capacity. Okay, so I'm looking at this definition of the Markovianity because it's channel capacity what I'm interested in, which I define. You know, so the Markovianity in my case is defined in terms of the channel capacity. Now, if you ask me if there is a connection with the form of the spectrum and this behavior, then in general there is no connection between, for example, a structured spectra and the presence of oscillation. So there is no connection between this definition or all the other definitions of the Markovianity and the form of the spectrum. It is not said that. So there are examples, to be more precise, there are examples of extremely structured spectra which lead to still Markovian behavior in terms of BLP, or in our case also. So really completely spectra which even have oscillations, which are Markovian in terms of BLP trace distance, and also in our case. So this is absolutely, for pure differentiating, we have necessary and sufficient conditions on the form of the spectrum to have backflow of information in BLP sense. But other than that, I don't think that there is, as far as I know, there is no connection general.
Other questions?
Could you repeat why distinguishability is related with the backflow of information?
Yes, so this is your question.
Yeah.
This was also my question, in fact. So the thing is, what they did is the following thing. So they assume that if I'm able to distinguish more to distinguish well quantum states, then I know, not they assume, this is the interpretation of distinguishability as a measure of information, and it's really universal. You find it in the books. So the more I'm able to distinguish quantum states, the more information I have on the state. So in this sense, the definition of using distinguishability to quantify the amount of information on the system is sort of, it's something that, let's say, it is given, it is the definition itself. If I want to consider the concept of information flow, what I can say, what I can see, is that because of the contractility property, whenever a quantum system interacts with an environment, then the distinguishability between the two states always diminishes. If the distinguishability diminishes, then I can imagine that what happens is that, not I can imagine, I can, according to the definition before, I can say that I know less and less about the state, because my distinguishability is diminishing. And why I know less and less? Because there is the environment that is continuously monitoring the system, and therefore it's extracting information on the system, and therefore I'm losing information on the system, and therefore I have less information. This is associated to the mathematical contractility property of trace systems. So therefore what they did was to associate, what they defined basically, non-Markovianity in terms of information flow. But there is nothing more than this. And as I said before, because I used it extensively, this definition, and also this definition, and also Roberta was mentioning, but I do always say information, and it's true. But when we started to look more in detail to what the quantum information community did, then we started to wonder, but are we really entitled to say this is information going from the system to the environment and back? And we think that there is no law of conservation of information between system and environment. It's not true that if I use information, it's not information, amount of information of the system plus amount of information equal to constant. This is not true. So, well, the only thing I can say is that I'm using information on the system in the sense that I can distinguish less and less the states.
But you can use other quantities like the relative entropy?
In the original paper, they also looked at the relative entropy, and there are several reasons why they didn't use relative entropy to define the measure. One of them is that it is not symmetric, so they wanted to have a measure that was the same. The distance to and distance from was the same. And then I think that they had difficulties also because of some divergences in the relative entropy for some of the cases that they didn't want to have. But I'm sure that one of the reasons was, so they defined certain criteria that according to them a good measure should have, and one of them was the symmetry. And just satisfy this. Fernando?
It seems that it's very much centered in the information flow. But if you want to talk about memory of the path with respect to the past of the system, why don't you use like the mutual information of the path at time t with respect to past states of the system? Or something like this.
Cost. Sorry?
The mutual system and path are different.
Mutual information of the path with respect to the system in the past.
Yeah, well, of course, this is also a possibility. What we wanted to do is to start from the simplest way of quantifying, defining a quantity that connected basically the concept of accessible information, which is what is used in quantum information theory, and yet when I use the quantum mutual information, I'm interpreting this as the accessible information on the output state, or the accessible information on the input state that I have after the state is passed through the channel. And if I do this, what we simply saw that basically this contained entropy, fundamental entropy of the final state, which measures the amount of information of the final state. Final state means the whole state, and exchange entropy, which by definition is equal to the variation of entropy in the system. So we just wanted to use the simplest possible formulation, while obviously, in principle, you can think of many other, and obviously we wanted to have something that was linked to quantities that are used in quantum information theory, like for example the channel capacities that have an operational interpretation, and they are used to give bounds on
But nobody is measuring memory.
No, what happens is that it's not really what is measuring memory. This is something important. There exists memory kernel master equations that in terms of divisibility, for example, are completely Markovian. So in terms of information leaking from the system, and I'm talking about a memory kernel master equation, which in principle should give me you assume that is a memory because it's an integral differential equation, so I have a kernel of memory and so on. And still, in terms of information content on the system, the information flow goes simply out. So, I mean, my feeling is that the idea that we have of connecting, let's say, the state of the system at time, so it is not true in general that I need to have a connection between the state of the system at time t and its past state to have, let's say, non-monotonicity or to have, let's say, memory effects in the system. The simplest case is exactly the Jennings coming model. Okay? I mean, the Jennings coming model is a case in which you really have, it's clear the memory effect, because you have the photon is exchanged between the system and the environment, basically. If this is really a very peaked Lorentzian, I mean, what is it? And the master equation is time local. Why do you want to connect it with the past state? Everything is time local.
It was in the list of possible definitions.
Oh well, yes. It's still an open possibility. But I mean, then I think that if you would define it in this way, I would tell you in here. Okay.
Other questions or comments? If not, we can thank Sabrina again.
It's not obvious, no, that the definition is time local. That you will see. Are you sure that a time local kernel or equation will give you?
Oh, I don't know.